Non-Stochastic multiplayer multi-arm bandits. This is a joint work with Sebastien, Mark, and Yuval. And the paper is online now on arXiv. Multi-arm bandit problem is a very famous problem of modeling how to make sequential decision online. Usually there is one player with multiple arms, and there are machines where the player can pull the arms to obtain certain reward. We assume that there are K arms and there are T rungs, and at each run T, the player is going to pick an action AT along those arms, and then observe a reward RT of AT of the associated arms at this iteration, between 0 and 1. And the goal of the multi-arm bandit problem is to maximize the total accumulated reward across the T iterations or the T runs. And the question we consider in this paper is, what if there are multiple players playing in the same environment? So there's player 1 and player 2. Player 1 is pulling those arms, and the player 2 are pulling the same set of arms together with player 1. And the central issue is typically when the two players actually pick the same action at the same run, they will only be able to get one piece of reward in total because there is only one machine that gives the reward. And that means if the player A picks action AT at run T and player B pick action BT at run T, and when AT is equal to BT equal to some action A, they are only able to get one piece of total reward instead of RT of AT plus RT of BT. So if the two players pick the same arm at the same iteration, they are only going to get one piece of reward instead of two. And so the main observation is that in this case, since all the rewards are non-negative, to maximize the total accumulated rewards among all the players, it is really important that all the players pick different actions at the same run. So they should avoid picking the same action at the same run. And we call this strategy a non-creation strategy if all the players pick different actions at the same run. And we define the regret of the non-creation strategy for M players, multi-arm bandit, as the difference between the maximum reward that you can have by playing a fixed non-creation strategy comparing to a sequence of non-creation strategies, where we assume that at each iteration, all the players pick different actions. So this is a non-creation strategy. And we want our adaptive strategy to be as well as the best prescribed strategy on the hand side. And now the question is, can we get a regret root T algorithm without any collisions? And there is actually a very simple strategy that can achieve that, which is we can have a central server which picks a subset ST of size M, where M is the number of players at every iteration. Then you just communicate with all the players about this set ST, and the players pick actions in this ST, maybe according to the smallest to largest. Then they will have no collision, and only the central server need to play the game. So it can achieve regret root T. But the main problem is this strategy requires the players to communicate at every iteration. So the total bits of communication is omega of T because there are T total runs. The communication costs are too high. In many multiplayer multi-arm bandit settings, the communication is rather limited. So you really want to minimize the total number of total bits of communication while getting the same small regret. So the main problem considered in this work is, can we actually get a root T regret algorithm without collisions with smaller communication costs than order of T? And this is really challenging since there is actually a fundamental dilemma. That is, if the player do not communicate at one round, how do they collaborate with the other players to make sure that there is no collision? Okay, and this, recall, our setting is the so-called adversarial multi-arm bandit setting. So players have to constantly performing explorations, and they cannot stick to some fixed action. Okay, typically, adversarial multi-arm bandit strategy looks like this, where the players switch between different arms to perform exploration. And actually, you can show regrets or show a lower bound that if the player does not switch very frequently or does not switch essentially every round, then it cannot achieve regret routine. Okay, so the players have to switch around the arms for exploration, but they also want to collaborate with other players so they do not pick the same arm. And this is challenging, but still in this work, we show the following main result, that there is actually an efficient routine regret algorithm without collision, with only routine bits of communication. Okay, and we shall illustrate the main idea of this algorithm in our paper in the two-player setting. So there is player Seb and player Mark. And the main idea to achieve this lower communication cost is that the player Seb actually uses a low switching strategy that only switches arms approximately every routine iterations. And when Seb switches the arm, he is going to tell player Mark which arm he is going to pick. Okay, and then player Mark actually knows which arm the Seb is going to do in this routine many of iterations. So the player Mark can then place on the remaining set of arms to avoid collision. Okay, so the strategy looks like this, where the player purple action is the player Seb's action. You see player Seb is switching his action very infrequently, so he is only switching only every routine iterations. On the other hand, player Mark is switching his action very frequently, so player Mark is switching his action and exploring on the remaining set of arms. However, there is a main issue of this simple strategy, which is if player Seb uses a low switching strategy that only switches arm approximately every routine iteration, then he will not have enough exploration. So how does he know which arm is good? He does not have enough exploration on the other arms. He's fixing his action in this set of in this very small set of arms. Okay, he's switching his action very infrequently, so doesn't really explore the space very well. And so to fix that, we propose our next new idea, which is the player Mark actually does the exploration on the remaining arms. So although player Seb does not explore the other arms very well, but player Mark actually explores the other arms very good. So when player Seb decides to switch arm, player Mark is actually going to tell Seb about the estimated accumulated odds on all the other arms. And then the player Seb knows enough information about the remaining arms, although he doesn't really pick them, but player arm can tell him about the accumulated loss. So player Seb can actually know enough information about the loss of the other arms, so he can pick the next arm according to this information. So in total, the game looks like this. The Seb is going to play a low switching strategy, and then the Seb can tell us, after Seb decides to switch, Seb tells Mark about the accumulated reward or the loss of this arm, and the Mark actually tells Seb the accumulated reward or the loss of all the other arms, or some estimated accumulated reward within the set of iteration where Seb plays the same action. Okay, in this way, they exchange very few bits of message, but they still have enough exploration to get a routine regret algorithm.